right, so let's talk about triple integrals. Now, let's think about this, right? We can use a single integral to get the area under a curve. We can use a double integral to get the volume of a, the volume enclosed by like a surface over a region. Now, triple integrals, right? We're essentially, going each dimension, right? We use single integrals for 2D area, double integrals for 3D volume. What are we going to use triple integrals for? Well, if you think about what a triple integral is doing, it's basically over, we take double integrals, we find the volume over like a 2D region. Now, for a triple integral, we're finding, the sum of all values of a 3D function, right? If you think about or a 4D function, right? F of x, y, z, right? What we're doing is we take a volume, in this case, just to show you it's going to be as simple as a cube. We take or a box, I should say, and we take this box and we're splitting it up into like M kind of rows, N columns, and then kind of like O layers, right? Like the amount of layers up. And this is the 3D volume that we're essentially going to integrate over to get the total kind of value of all of the f of x, y, z's integrated times, right, our delta v, right? Because if we think about this, we have this delta v, which represents the volume of each of these little cubes that the box is split up into. And it just very simply equals delta x, delta y, and delta z. So when we go ahead and we want to find the total, the sum, the sum of all of the function values over this volume, essentially what we're doing is we're taking a triple sum. We're saying, hey, we're going to sum up f of x, y, z times change in volume, right? To find regular volume, we're taking the height, which in this case, like if you think about double integral, we're to find the volume, we're taking the height, which is given by f as a function of x and y, times delta area, right? So to the next dimension, we're going to take not really the height, but we're going to take a 4D variable and multiply it by not delta area, but this time delta volume. That's how we go to the next dimension, essentially. So it's going to be a triple sum, right? Because it's a if we think about it, we're going to sum up, we're going to get all the rows, right? Like let's just, let me write the bounds. We're going to say I equals 0 to m, j equals 0 to n, and then k equals 0 to o, right? So we're essentially going from, or you could say equal to 1, what doesn't really matter, but I think, because it doesn't include this, I don't believe. Might be wrong on that. But the idea is like, hey, we're going from 0 to m, 0 to m, 0 to m, 0 to m, 0 to n. We're summing up this quantity, right, along 0 to m from all the way from 0 to n. And then by the time we get to here, or I guess to here, we restart to the next layer, right? 0 to m, 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 going all the way from 0 to n, and then we go to the next layer all the way from 0 to o, right? That's why we're kind of using a triple sum, right? We're gonna, for each layer and for each column and for each row, we sum this up and we get our total, or at least an estimate, right? Because to get a better and better estimate, we need, right, to take the limit as m, n, and o approach infinity, right? We want to slice this volume up, or solid, I guess you can think of it as solid, into infinite rows, columns, and layers, I guess. And that way we get our actual double integral, right? Or the triple integral, I should say. Triple integral over a region E, f of x, y, z, dv. Now, there are going to be a couple of different regions, right? It's very similar. So let's just think about this. Essentially, this is what we call type 1. And for a type 1 integral, what you're doing is you're essentially doing, right, a double integral over a region R in the xy plane. And this could be like a type 1 region or type 2 region, this region R that we talked about before. We're essentially taking the double integral of the integral from the top surface z1 to the bottom surface z2 right? So if we put like a little bracket, f of x, y, z dz times dA, right? That's how we make this a triple integral. We're going to do the top surface minus the bottom surface over this region R. So it's going to end, that's how our triple integral ends up being. And you can imagine for these regions, this is what we call a type 2 solid and a type 3 solid. Now, this will end up being, some, and z1 and z2, these are functions, right? Functions of f of x, y, right? So now we will have functions, when we're kind of integrating over a region in the zx plane, right? It's going to be the same double integral. It's just now our double integral is now kind of going to be taken in the x or xz plane, and it's going to be the same thing where we're going to have an integral inside this double integral from y1 to y2 f of x, y, z dy times dA, right? And then this dA, right, is just taking a regular double integral, right? So this could be dx dz, this could be dz dx, depending on whether it's type 1, type 2, or whatever. And you can imagine it's going to be the same thing for type 3, but we're going to integrate with dx first, right? And then we're going to have like x1 minus x2, where these are functions of, right? At y2 is a function of x and z, which is kind of crazy to think about. You don't need to worry about this too much, but this is just to get kind of an intuition, right? Essentially what we're doing is we're taking the top minus bottom and we're integrating down, and then we integrate it over the full region using the double integral, right? Or we're integrating from kind of left to right, or like kind of, furthest from the x-axis to closest to the x-axis. That's what the inner integral represents, and then we take a double integral over a region in a plane. If that kind of makes sense. Don't worry about it too much. I think solving triple integrals is not that bad. So for an example, let's say that we had to find this double integral. So we have double integral over a solid E or region E. Double integral over this region E. And let's say it's x, or let's say it's y times z times cosine x to the 5th dv, where E equals x, y, z, and then let's say 0 needs to be less than or equal to x, less than or equal to 1, and then let's say 0 needs to be less than or equal to y and less than or equal to x, and then let's say x needs to be less than or equal to z, which is less than or equal to 2z. So what these inequalities right here describe the region over we're integrating, right? A lot of people might be tempted, not tempted, it's not a lot of people, but, people might be thinking, oh, is this a region I'm integrating over? And then they draw this region. That I've honestly done that a couple times, because sometimes this will only be, like, sometimes they won't add that cosine x to the 5th, right? It'll sometimes be y to the z, or y times z only, and you think, oh, they won't include the z, so it'll be y times cosine x to the 5th, right? That's still, so there was a little pause there because my phone did this weird thing where it wouldn't record, I guess, the entire thing because it's storage. So this is day 2 of triple integrals. What I was talking about before it cut off was just that, sometimes the inner function, or the function you're integrating, right, f of x, y, z, sometimes it'll be only in terms of y and x, right? Take away the z, y cosine x to the 5th, and obviously that would be hard to graph, regardless. But, if it is in terms of x and y, that's not the region, right? Sometimes you might draw that region, and that's not the region you want to, that's not the region over we're integrating. This is the region. This is just simply the function that we're integrating, if that makes sense, right? And yeah, so let's get an idea of what the region looks like. If we draw this out, x is going to be between 0 and 1, and y is going to be less than x. So if you think about drawing the line y equals x, right? So if I imagine this right here, y equals x. yeah, y equals x. I don't know why that took me a second to just register what I was doing there. It's going to be all values less than that, right? Because y needs to end up being less than x. So if we think about our region, it's going to look kind of like that. It's going to be like this triangle. And we're going to have the z values, right? So the z values are going to be in between z equals x. Okay, we can draw it like this. Z equals x, and then z equals 2x. So remember, these are planes, right? These are really planes that pass through the lines z equals 2x and z equals x. So if we extend this out into 3D, you get something like this. It's a little hard to kind of visualize, in all honesty, and draw. But the idea is that we're going to look at z values in between. So when we're setting up our integral, right, first of all, you notice that, hey, there's a cosine x to the fifth, which I can't really integrate. It would be really hard to do that. It would be nice if we could do u sub, right? So what we're going to do is we're going to do, right, dv, I think I probably might have talked about this before, but dz dx dy is the same as dy dx dz, right? Those both represent the change in volume. So I'm going to do dx last, so hopefully by the time I get to that point, I have a term x to the fourth. And I think I will, right? Because I'm going to end up integrating y dy, which is 1/2 y squared plus c, and then, you know, z dz 1/2 z squared dz, which will end up being in terms of x. So we'll see how this pans out. So y z cosine x to the fifth. Let's just do dz dy dx just for simplicity, right? This you could probably get away with, you know, this could, I think, you know, this could be multiple types, right? This could be like this could really be type 1, type 2, type 3, but we're just going to do dz first because it's pretty easy to see. We can do the top surface minus the bottom surface, so 2x x. And then for the y values, right? Remember this integral right here, the first integral we take with respect to z, that ends up being, well, after that, this just ends up being a double integral over a region, right? So over our region, it's going to be, this is the region we're integrating over. So the top, just like we do for double integrals, the top, you know, y function is going to be y equals x. So we're going from x to 0, because the bottom is just y equals 0. And then we're going for, finally, dx, we're going from 1 to 0, right? Because we're only going up until x equals 1. So this would be 1, 1. Let's do this. So we can pull, you know how it is. You can pull the y cosine x to the fifth out of the first integral. And then for the second integral, right, we're going to get a 1/2 z squared. So I'm going to get 1/2 z squared, right, when I'm doing z dz, right? So 1/2 z squared, that's going to be 1/2 2x squared minus 1/2 x squared dy dx. And I can pull the 1/2 out of this integral, out of both of the integrals, really. And what I'm left with is I'm going to have, well, what I can even do is this right here, when I evaluate this, this is going to be terms of x, right? And we have the cosine x to the fifth. I can pull this out just for simplicity's sake. Oh my God. Pull this out of the first kind of integral we had going on. So cosine x to the fifth times 1/2 we don't have to worry about. So it's going to be, oh, this is 2x squared. My fault. So 4x squared minus x squared is going to be 3x squared, which I can also pull out into the front here because it's a constant with respect to all variables. And cosine x to the fifth times x squared. I'm left with now integral from x is 0, y dy dx. And you're going to see it's going to be 1/2 y squared, that's the antiderivative, plus c. And then we're going to have 1/2, substitute the x in because of FTC. This is all FTC, right? Fundamental theorem of calculus. I'm going to get 1/2 x squared. So times 1/2 x squared. I see I have another 1/2 here, so I can pull that out, and I get 3/4 in front. Now I have this x to the fourth. And now I can do my u sub, right? I have x to the fifth and x to the fourth. So if I set u equal to x to the fifth, I have to change the bounds, which I'll do in a second. du is going to be 5x to the fourth dx. And I get 1/5 du is going to equal x to the fourth dx, which is pretty cool. And then, well, you know, when I substitute this all back in, I'm going to have this 1/5, right? 1/5 du for here. So I could pull the 1/5 out, right? So I get 3/4 times 1/5. That's just 3/20. 1 to 0, right? For our bounds, we don't even have to change those just in this case, because when I do 1 to the 5th, I get 1. When I go 0 to the 5th, I get 0. So it ends up being the same. But I get cosine u du. And my derivative of that is pretty simple. It's going to end up being sine u plus c. So I'm going to get sine 1 minus sine 0. Sine 0 is just 0, so I get 3/20 sine 1. Awesome. And let me make sure that whole thing recorded. I'll be a little bit ticked off if it didn't. Okay, my phone's working again. All right, so now what I want to do, and also let me just check my hair. Hopefully it's not too bad. It's been kind of crazy recently. It's just hard to maintain. What we're going to do now, I want to talk about, so I can go through triple integrals all day, right? The hardest part about triple integrals is just finding out what are your bounds, right? Like what bounds should you do? After that, it's just good old integrals, right? It's just taking antiderivatives. So what I'm going to do is I'm going to do a little example of what we call changing the order, right? In the same way that we can go dy dx and dx dy, you can go dz dx dy. There's 6 combinations that equal the same thing. That's just 3 factorial. So I'm going to do an example of going through finding all the orders of integration for a certain thing. And this is taken from Math 2 through 4, which is Michigan State's Calc 3 class. So thanks to the guys over there. Let's consider the following integral. So it's going to be, the bounds are going to be from 0 to 1 minus y, integral 1 to x squared, and integral 1 to negative 1, dz dy dx. So first thing I want you to just draw your attention to is the fact that the function that we're integrating is just like f of x, y, z equals 1, right? It's 1 dz dy dx, right? It's not implied, but it's implied because we don't see anything there. So it's 1 times dz dy dx. This ends up actually this computes the volume of the region that you're integrating over, right? In the same way that you can find, how do you think about double integrals, right? A double integral finds volume. But what if your kind of function that you're integrating under, right, is just z equals 1, right? Well, when you do base times height, base, which ends up being the area of your region, times the height, which is 1, well, the volume numerically will just equal the area, right? They're really not the same thing because of dimensional analysis, I think, but like numerically it's the same number. So the numerical answer to this is going to be it's going to be equal to the volume. This is not really computing the volume, but it is. It basically is, okay? Let's just think of it like that. I don't need to complicate this. So let's just draw the region. Now first, here's how you want to think about this, right? Okay, well, I'm going from the z function 1 minus y to 0. So 1 minus y, that is a plane that contains the line. Like if you think about the line, if I were to graph z equals 1 minus y, that's what it would look like. So I'm actually going to draw 3 graphs, and you'll see in a second what they're going to represent. But if I were to graph z to y in this 2D it's in a rectangular coordinate system, I get this line 1 minus y with the y-intercept 1 and slope negative 1. So if I were to extend this to a plane, right, I would get something kind of like this. Now, the next thing for my y value, right, the region that I'm integrating over, right, remember, this first integral is finding kind of like, it has to do with difference in height. After that, you're just integrating over a region. So the region that we're integrating over is going to have, the y kind of bounds are going to be 1 and then x squared. So let's think about this. Let's do y to x. The top is going to be 1, and then the bottom is going to be x squared. So it's going to be this region right here. But what you notice is I'm going from 1 to -1. So that just means that I'm going to extend this, over to -1. And the -1 squared and 1 squared is just 1. So it's just 1, -1, or 1, 1, -1, 1. All right. We'll talk about this bottom graph maybe in a second, but I don't want to throw too much. The idea is now that, okay, we can draw the parabola in the bottom like so. And then this gets kind of hard to draw, but essentially the plane, it's going to kind of, if you imagine like taking the cylinder, right? Imagine taking the parabola thing, like the parabolic cylinder that kind of slices down. That's the kind of shape we're working with. I wish I had like a 3D model or something of this, because I have trouble explaining this. It's like the backside of this shape is like this New York mug, but without the New York like it's just like a cylinder, and then it's like kind of flat, like on the top, right? You kind of cut but it's not really like this. It would be a parabola, like a parabolic mug, but you get what I mean. It's gonna be like a cylinder kind of thing, just parabolic. I should not do that. Oh boy, it's gonna be taken out of context, but yeah, whatever. It's fine. It's not a big deal. So let me just draw this, like getting rid of these lines, right? It's gonna kind of look like this. Yeah, okay, perfect. And then I can even draw like this over here. Cool. Let's change this out into each order, right? Let's start with the easiest one. What if we do dz and then just flip these two, right? So this is easy because I already know what the z bounds are. It's just going to be dz. Now let's go dx and then dy. Well, this is just this very simple thing we've done of changing the orders for double integrals, right? What I'm going to do is I'm just going to be like, okay, well, let's think about y equals x squared. Change it in terms of y, so I get plus or minus root y equals x. These represent positive values of x and y, so I know this side is going to be positive root y equals x, and the other side is going to be the negative values of x. So this is going to be negative root y. So I'm going from left to right, so I'm going from root y, so let's draw in our integral, root y to negative root y. And then I'm going from top to bottom, 1 to 0. Awesome, that was pretty simple. Now this is where you're going to kind of have to think about things, all right? Let's go with dy first. All right, let's think this through. If we're going with dy first, what we're really doing is we're integrating, if this is our y-axis, right? I always forget drawing in this, but we're essentially if we were to think about the lines of integration, we're essentially integrating like this, like so, right? We're going this way. So let's think about this. This is gonna be kind of hard. First of all, you notice that I went this way, right? I drew those lines, but then I started going along the x-axis. So that means I'm doing dx first. And then I would go to the next top level, and I would go, then that would be dz, right? So I'm going this way, this way, this way, and then I go up one, this way, this way, this way, so on and so forth. So the deal is well, y, right? This is our kind of, the plane ends up being our kind of to the right function, the surface farthest from the origin, and then the kind of parabola ends up being the back of this thing, which is really just a parabola, ends up being the bottom kind of surface, right? If you were to think about looking at it from the top. So, this plane, I just gotta get in terms of y. So z equals 1 minus y. This is just the same as y equals 1 minus z. So that's gonna be my top bound, 1 minus z. And then my bottom kind of bound, right? So my bottom bound. Remember, if I were to look at it as if this were the top, then the plane is the top, and the kind of cylinder, parabola, or parabolic cylinder ends up being the bottom. That's just y equals x squared. So I'm going from 1 minus z to x squared. And think about this, right? As we start going up and we're doing the same kind of integral, right? My bounds change by height, right? If I'm on this level and I start taking the integral, my bound is different because of the height, right? Before it was maybe, y equals 1, maybe here, this is y equals 1/2, right? It all depends on the z. So that makes sense. The top bound is 1 minus c, top bound is 1 minus c, and then x squared, that doesn't change with height, but that does change with x, right? At this x value, it's a different kind of bound of integration, right? I'm going top to bottom, much shorter than going from here to here. Hopefully that kind of conceptually makes sense. Then I'm going along dx. Now, remember, the next two integrals is just the region of integration. So my region of integration, this is going to be kind of hard to visualize. But think about it. If I were to think about the region of integration, I'm going along this parabola here, right? It's going to look something like this. Hopefully you can kind of visualize that, right? Because this kind of ridge represents the parabola, right? The region that I'm integrating over. So what's the equation of this parabola? This is where z, the z and x thing helps, right? If you were to think about this, it's going to be a negative because it's opening down, and it's going to have a positive thing. Well, hey, I know if y is equal to x squared, and y is just 1 minus z is equal to x squared, I get 1 minus x squared is equal to z. So my top curve is 1 minus x squared. My bottom is just 0. Oh, I'm sorry. Wait. I'm doing dx first. So I would have to think about, the left curve and the right curve, right? So if I were to rearrange, right, I get x squared is equal to 1 minus z. Take the square root, right? I get plus or minus that 1 minus z. So I get positive 1 minus z, and the bottom bound is negative 1 minus z integral. And then I'm going from 1 to 0, right? Because it's a dz, I'm going from 1 to 0. All right, now once again, I can make this easy by just doing dy first, so I don't have to worry too much about thinking about that. It's just dy, the same bounds. And if I'm doing dz first, this is where I would do, right, top curve minus bottom curve. So it's going to be 1 minus x squared to 0, and then I'm going from 1 to negative 1, as in my x's. So dy, dz, dx. Now let's do the last one, or the kind of last, pair, where you do dx first. So for dx, if we think about this, I'm going along the x-axis, so you can see, I think dx is a little bit hard to visualize, but it's gonna end up being, if we think about the cylinder, right? Remember, think about the cylinders, right? If I think about cylinders, and then flipping it, or no, I'm just thinking about this side versus this side, right? Because it's going to be kind of smooth all over like so. So I know y is going to equal x squared, and if I rearrange, I get x is equal to plus or minus root y. And this surface over here is a positive root y, and this over here is a negative root y, because I get negative values of x. So I'm going from root y to negative root y. And once again, this kind of, this makes sense because when I'm going from left to right, right? Let me erase this. If I'm going from left to right, or right to left, right? The bounds of integration don't depend on the height per se, right? When you get higher up, it's still only, you know, it's kind of weird because it's like you're integrating, when you're along the y-axis, you're integrating less, but along the x-axis, you're still integrating from root y to negative root y. So it doesn't depend on z. That's kind of the key idea. It's hard to think about, I know, and honestly, I'm not perfect at explaining it, as you can probably tell, but hopefully it's kind of clicking to you. Now remember, double integral, the path of integration matters. So really, I'm just going along this path of integration, right? The path of integration here, which is just this graph. So top curve, if we were to do dz first, top curve is just 1 minus y to 0. And then I'm going from 1 to 0. dy. And then if we just end this off, root y to negative root y for dy. Integral. And then now I just do y equals 1 minus z, right? For right to left. So 1 minus z to 0, dx and then dy. And then for dz, I'm going from top to bottom, 1 to 0. Awesome. Those are all the orders. So yeah, hopefully this kind of made sense. If it didn't, then let me know in the comments. Maybe I'll make another video specifically on, you know, changing the orders of integration. But yeah, thank you for watching. Hope all that drops. So, oh well, there you go.